Okay, so as temperature increases, particles have more energy, allowing collisions to form products. So C is the best answer for this one. I do want to note that if you increase temperature, it does not change the activation energy. There's only one thing in this class that's going to change the activation energy, and it's not temperature. All it does is allow you to get over the activation energy quicker and easier. It doesn't actually change the size of the hill. The hill size still remains the same. You can just get over it easier if you're at higher temperatures.
Screen sharing.
Oh. Okay, so solid particle size is for like heterogeneous mixtures, like you're taking a solid and dumping it in a solution, or you're taking a solid and dumping it in a liquid. And this could be a chemical reaction. It could just be dissolving as well. So when a solid reacts, the more surface area, so like the more spread out the solid is, like the finer it is, the more powdery it is, the faster it will react, as opposed to like a big huge chunk, because a big huge chunk doesn't have as much surface area. It only has the outside, but then there's a ton of solid on the inside of it that the liquid or whatever you're trying to mix it with doesn't have access to. So particle size plays a role. The finer or more powdery a solid, the faster it will react. So if you took like a huge baseball size of salt, it was 50 grams of salt, and you dropped it in water, or you took 50 grams of just normal table salt that isn't in this baseball chunk and you dumped it in water, the one that's just not in the baseball will dissolve faster, because the water can have more access to it because there's more surface area to it. So another like kind of everyday life example I try to use is, does anyone know, let's see, let's look at my chat. Does anyone know, yes, catalysts help lower the activation energy. Does anyone know what, anyone that has had like a heart issue, or like a has had maybe a heart attack before? Anyone on here? Okay, well, even if you don't know someone, do you know what they tell people who have had heart attacks or heart issues to keep on them? A medicine. It's an over-the-counter medicine. Okay, aspirin. So next, anybody know why aspirin? Do you know what aspirin does? Anyone? Anyone? Aspirin? Okay, it's a blood thinner, so it thins your blood. So why would this be important for a heart attack? Well, usually in a heart attack, your blood vessels are being constricted. So the thinner your blood is, the more easily it can pass through and still keep pumping blood, to your heart. So you take some sort of blood thinner, which is what aspirin is. And the crazy thing is guess what they tell you? Well, they don't always tell you. You can take aspirin in the pill form. It's just these like little white pills. But they sometimes recommend that you do what to the aspirin that you carry around with you? Smash it, right? Smash it into a powder. Why is that? It will get into your blood quicker, right? Which time is really important if you're having some sort of heart episode, right? So if you smash it and then you ingest it that way, it will get into your bloodstream faster, making your blood thinner faster, hopefully buying you time to get you to the hospital and get you the help that you need. So this is an exact concept that is totally all chemistry based. More surface area of the aspirin allows it to get in your blood quicker and buys you a little bit more time. It'll thin out your blood faster. It's a faster reaction rate. Okay, so this example is a data. It's just a data table, as well as they've graphed the data. And what they've done is they've taken calcium carbonate chips. They're just like little pebbles. That's why they call them chips. And they mix them with hydrochloric acid. So on this next slide I ask you to please write out the reaction between HCl and calcium carbonate. So let's see if we can do that. HCl and calcium carbonate. Do we remember how to write out that chemical reaction? Remember, this is a special one. It is why the bubble bath things are so powdery. Yes, the more powdery can produce the better bubbles. So salt, water, carbon dioxide. This is that special one. Carbonates with an acid get you three products: salt, water, and carbon dioxide. So they take these pieces, they're just like chunks of calcium carbonate. They look like little rocks, but they're white. Okay, they're little tiny, like little pebbles of calcium carbonate. You dump it in HCl, you get salt water, and then a gas is produced. So you'll see bubbling happen. Okay, so what they did is on here, they have this red line, which they say were the large chips, meaning they were like the bigger chunks of calcium carbonate. And the blue ones were the small chips, so like the tinier pieces, maybe more powdery, all right? And they kind of graphed them over time. So they said volume versus time. So volume versus time. The volume was measured in milliliters of the gas, so they collected the gas, and the time was measured in seconds. So they probably just used like a stopwatch to do this. What can be deduced, that just means figured out, okay, about the total mass of the chips relative to one another used in each experiment. So, meaning the starting mass of the large chips and the starting mass of the blue chips, that's what they're saying, relative to one another. Do you think that you had more of the red chips, more mass, more of the blue chips, or the same, and why? So like if I had 50 grams of the big chips, oops, I'll do that in red. To start off with, I dumped 50 grams of calcium carbonate of the big chips into the HCl. How much do you think of the small chips I used? What kind of mass do you think? The same. Likely 50 grams. Same amount, same starting masses. Why did you think that? Okay, so it starts at the same spot, but it also ends at the same spot. Meaning if you look closer on this chart, the final volume collected for both chips was the same. Meaning if you're collecting the final product in the same amount, likely your starting product or starting amounts were also the same amount. The size of the chip didn't determine your overall outcome. You still got the same output. It's just how quick you got there was different. Okay? So most likely their masses were the same, meaning if you put in 25 grams of the large chips, you likely also put in 25 grams of the small chips because you ended up making the same amount of gas. All right. So the next question says, what are, or how long did each experiment take to go to completion, and how can you tell? So if you go back to here, we can also look at the chart, and we can look at the table. Both ways will tell you. If you look at the chart, the blue one, which are the small chips, you see it start to flatten out sooner, meaning it just stopped making more product, so it was over quicker. You reached the end faster. As opposed to the red didn't flatten out until a little later when it stopped. So the blue, the small chips, went faster than the red chips. But then even if you look at the actual data table, so if you look at 120, you had 79 milliliters of gas. At 135, you had 80, and then 80, and then 80, and 80. So the small chips stopped around 135 seconds. That reaction was finished. Whereas at 135 seconds and on, the red chips, the bigger ones, were still making gas. So the red ones didn't start being consistent until 165. So about a 30-second difference of the reaction being over. Okay, so this is this reaction with the small chips happened quicker. Why? More surface area is going to speed up the reaction. In fact, look how steep this curve is. Look how quickly the gas was produced for the blue chips because of more surface area, as opposed to this guy kind of lagged behind. It didn't make gas as fast. Now, they all still ended up making the same amount, but one just went faster. Okay. What are the possible units of rate of reaction? So for this class, and for this is going to be change in volume over change in time. That's how a rate is for this one. The other thing that we will use, which we're using volume because this is a gas, but if we're doing solutions, it will be change in concentration, molarity, over change in time. And that's rate. The rate at which you drive is measured in change in distance over time, miles per hour. That's a rate. But for reactions, we're doing changes in concentration over changes in time, change in volume over change in time. Okay. So this link doesn't work anymore, so I'm going to just pull up what I have. One way we collect gas in here is over water and the displacement of water, but another way you can collect gases in here is you can take like your liquid, right? Let's say this is HCl, and then we dump the calcium carbonate in here, right? It produces carbon dioxide gas. Now, instead of collecting the gas over water, we have what's called a gas syringe. So if you don't remember, I'll show you the apparatus. This syringe would have started with it totally closed, like the gray would be all the way up here. And then the more carbon dioxide that comes out, right, gases have pressure, so they push along and push the syringe out and out and out until you've collected all the gas from the experiment. So again, you would do the time, and then you would wait for the reaction to stop, and then this syringe has markings on it so you can read the volume of gas being collected. It's a slightly different apparatus setup that has all of the things described in this link right here. So how could you modify the experiment to do like concentration or temperature? So you could just pick one of them, either the small chips or the large chips, and then you could do the reaction at different temperatures. You could do a lower temperature, a higher temperature, and graph the rate of the reaction. If you want to change the concentration, the calcium carbonate won't help with that because the calcium carbonate is solid. So changing the concentration should be done with the HCl. So maybe you can use, the original problem used 1 molar, so maybe you could use 0.5 molar, lower concentration, and see how fast the reaction goes. And then you could also use 2 molar to see how fast the reaction goes, right? The 0.5 molar should go slower, and the 2 molar should go faster. So it'd be pretty easy to mess with both of those variables and just measure over time. Okay. So someone already mentioned this, but the way we can change activation energy is a catalyst. So none of those things can change the activation energy. They can help you get over the activation energy easier and quicker, but the only thing right now in this class that can lower our activation energy or make that hill shrink down is a catalyst. And they usually do this by providing an alternate pathway for the reactants to run into each other. So sometimes reactions are really slow. They don't like run into each other the right way. They're really hard to do. So you put some sort of catalyst in to kind of help facilitate the reaction to happen. Okay. And what they do is they make the hill lower. If the hill's lower, it's easier to get over. So we have this practice FRQ from a long, long time ago. It says the two reactions are represented above. These are obviously not real chemicals. These are just generic letters. And they show you a potential energy diagram complete for reaction 1, this guy right here. And they tell you that they start reaction 2 on here. So reaction 2 is right here. And they tell you that reaction 2 is endothermic, and that the activation energy of reaction 1, so the one that's actually drawn, is bigger than reaction 2. It says complete the potential energy diagram for reaction 2. Well, let's look at reaction 1. Remember, activation energy is your, it's so hard to draw a straight line, is your reactants to your top of the hill. So that's for reaction 1. Well, if they tell you reaction 1's activation energy is bigger than 2, the second one, then you need to make your second hill smaller because it has a lower activation energy. Now, it doesn't ask you this, but reaction 1 is endo or exothermic for profile 1. They tell you reaction 2 is endo, but this is energy being lost, right? Released, lost, given off. So the profile for energy for reaction 1 is exothermic. Now they want you to have reaction 2 be endothermic, which means your products have to have more energy than your reactants, not less. So I have to make it with a smaller hill, and I have to have my products have more energy than my reactants. Okay, so again, I'll put fake numbers in here. Let's call this 10. Let's call this 20. Oops. And so then you have 2xy over here. Those are my products. This is definitely a lower hill, right? And again, so if this is endothermic, delta H, which is products minus reactants, endothermic, it should be positive, right? So I put fake numbers in here. My products are higher than my reactants. So my products are 20, my reactants are 10. That's a positive 10, endothermic. Okay. It says for reaction 1, predict how the following is affected as temperature is increased. So if you increase temperature, what happens to the rate of the reaction? Can you predict what would happen to it? It should speed up, right? If you increase the temperature, the molecules move faster. If they move faster, the rate of the reaction will increase. Okay, this is the harder one. The heat of the reaction. Now remember, heat and temperature are not the same thing. A gallon of water at 100 degrees Celsius is not the same as a drop of water at 100 degrees Celsius. They're both the same temperature, but they do not contain the same amount of heat. So when they say heat of reaction, they're talking about this guy, delta H. Yes, the temperature goes up, but what happens to the delta H? Nothing. Nothing is going to happen to the delta H. You will start and end in the same location. You might get there faster, but your beginning spot and your final spot will be in the same location. Okay, so how does a reaction proceed? They're called reaction mechanisms, and reaction mechanisms are just a step-by-step process that allow you to show you the way a reactant gets to a product. You're only as fast as your slowest step. So far, when we've looked at chemical reactions, we've only looked at the overall reaction, reactants to products. But the thing is most reactions don't go from reactants straight to products. They do something here, then they go off and do something here, and then you get to the products at the end. So we have to look at that this chapter instead of just an overall reaction. So all those steps combine to make your overall step, and whoever your slow step is determines your rate. It's known as the rate determining step. So all of the little baby reactions that make up the overall reaction are called elementary reactions. And each of those have like what are called molecularities. And all it means is they want to know how many molecules of the reactants are running into each other. So for example, right here, there's only one molecule. So it's called a unimolecular step. There's one molecule. For this one, there's two molecules running into each other. So it's called a bimolecular step. Well, it's hard to see because that other thing. The bottom one down below says 2NO2, or I'm sorry, 2NO and O2. So that's three things running into each other. Two of the NOs and then the O2. So it's a termolecular step. Those collisions are rare, right? Because so not only do you have to get all three molecules to collide, they have to collide with the right orientation, and they have to have a certain amount of energy. So those are harder to do. It's not that they don't happen, they're just not as common, okay? So we're going to do a sample mechanism. It is proposed that ozone gets converted to oxygen in more than one step, actually 2 steps, all right? So here's the steps that they're proposing. This is a proposed mechanism, a step-by-step process. This is elementary step 1, elementary step 2. So let's talk about molecularity. So this first step, how many reactants are there? there's one, right? So that would be called unimolecular. That's it. Now, step 2, there are 2 molecules bumping into each other to make product. So that would be a bimolecular step. Okay. All right. When we look at our mechanisms, we will end up writing rate laws, and the rate laws are going to be based on reactants only. So a rate law will always go like this: rate equals K, and K is a rate law constant, okay? You will only have reactants in the rate law because only reactants determine how fast or slow a reaction goes. Products do not determine how fast or slow a reaction goes. Who you have at the beginning is going to determine how fast or slow you're going to go. So when we write rate laws, the rate depends, or the rate or the speed depends on reactants only. You will only ever see reactants in there. And then they will be raised to these little exponents right here that are going to be called orders. This is going to make more sense when we actually write rate laws, which isn't going to happen today, but we will go more into it. But all of our mechanisms can be helped to write rate laws, the rate or the speed of a reaction. Now, if we have our elementary steps without any other information, so look at, you have A, one reactant. The rate law would be rate equals K, always, and then times the concentration of A, because this is unimolecular. There's only one substance. But look here, we have 2 reactants, right? A, B. So now my rate law has A times B in it. Both of them are in it because both are reacting. What if you have 2 A's? Well, it would be the same as writing rate equals K, A times A, which is the same as A to the second power. What if you have 3 reactants? 1, 2, 3. Well, the rate law equals rate equals K, A times B times C, because now we have 3 reactants. All right, rate equals AAB. So when you write the rate law, you have A squared, because there's 2 A's, and a B. This one has 1, 2, 3 A's. So A times A times A. Rate equals A times A times A, which is the same thing as A cubed. And again, they all start the same. Rate equals K, rate equals K, always. Now, this way where we're using the reaction to write the rate law is not the most common way to do it. In fact, it's going to be the last way you would ever do it. But for now, the stoichiometry, or the balanced reaction, can't tell you a rate law. There's only going to be 2 ways to do a rate law. One is from mechanisms, which we haven't done yet, and the other is from data, which is going to involve math, and we have not done that yet either. Sometimes the rate law will match the balanced reaction. It's a coincidence, okay? The K constant is going to be asked almost always on the AP test to be calculated with units. And the issue with that becomes this. If this is my rate law for one reaction, but then like another reaction, my rate law is this. Different rate laws for different reactions. If I were to rearrange to solve for K here, and I were to rearrange and solve for K here, these units here are not going to be the same as these units because these rate laws are different. So there is not a set unit for K. There's no, like molarity is big M. It's always big M. It's a set unit. K does not have set units. So because of that, the College Board always likes you to calculate K with units. And that's the main problem. They almost always grade for units because the units can't be memorized. Like molarity is always big M. It's nothing else for the sake of this class. So you can't memorize the little K's units. It doesn't have a set unit because the rate law isn't set. It isn't always this, and it isn't always this. It can change, as we'll see later, okay? If you have a reactant that has no effect on the speed of the reaction, now that doesn't mean it doesn't participate in the reaction. It just doesn't change how fast or slow the reaction goes. It has 0 effect, so we call it an order of 0. So it looks like this, rate equals K, some reactant A Zero effect. Well, anything to the 0 power is what number? 1, right? So that substance is usually omitted from the rate law. Now, do not forget though, it is still in the reaction. It just doesn't determine the speed of the reaction. It's still part of the chemical reaction. It just doesn't affect the rate of the reaction. Okay? Now, in this class, our orders will be 0, 1, 2, or 3. They can be fractional, but we won't do them. So even though we're going to do 0, 1, 2, and 3 in here, these are the only ones we're going to do. This is the only ones you're required to understand. It doesn't mean that there aren't others. It's just what I'm telling you. There can be fractions, there can be other orders, but we are only going to focus on the nicer whole number ones, okay? When you have a mechanism, the sum of all of the individual steps, so step 1, step 2, step 3, all combine to give you the overall reaction, which is what we're used to seeing. So until now, we're used to seeing reactants, products, and nothing in the middle. So what we need to do now is we need to practice how do we write an overall reaction from a mechanism. So here we go. This is just like Hess's law, and it's also very similar to redox, where things on opposite sides of the reaction arrow cancel and things on the same side get added together to give us our overall thing. It's the same concept. So who is something you see on opposite sides of the reaction arrow that could cancel in this two-step mechanism? How about O on the right and O on the left? Monoatomic O at that matter, right? This guy and this guy. This is a product and then it's a reactant, so it cancels. Anybody else? I don't see anybody else, right? So what do I have left? Well, I have O3 on the left side, and I have another O3. So I have two O3s on the left. What do I have on the product side? O2, and then two more O2s. What's that a total of? One here and two here is three O2s, right? This is what we're used to seeing. Ozone decomposing to oxygen. But in fact, it doesn't just do this. It does a couple of things in between. So this is our overall reaction that we're used to seeing, and this is the mechanism that made it. Questions so far? So an O2 here, one, there's just one of them, right? And then there's two more right here, right? So that adds up to 3. Remember, things on the same side get added together and things on opposite sides cancel out or are subtractive. Does that help? Okay. Okay, now what we've never paid attention to in here are intermediates. Intermediates are substances that are produced in one of the steps and then consumed, reused later. So they come out as a product and then they go back in as a reactant, okay? They're generally unstable. They don't usually hang out for very long. And because they're on opposite sides, you don't see intermediates in the overall reaction, but that doesn't mean that they weren't formed and then reconsumed. So you have to actually do the experiment to figure out if there are any intermediates, okay? The opposite of an intermediate is a catalyst. So catalysts start off the reaction. The whole point of a catalyst is to get a reaction to occur. So you will see the catalyst right at the beginning of the reaction go in, but it will come out as a product at the end of the reaction unchanged. It doesn't change its identity because catalysts don't actually behave chemically. They aren't affected chemically in the reaction. They are put in and then they come out unchanged. All they do is help the reaction go, but they aren't actually participating in the chemical reaction. So because of that, you don't see catalysts in an overall reaction either. You can see them in the mechanisms, but you won't see a catalyst or an intermediate in an overall reaction. So back to the mechanism. Do you see a substance that goes in and comes out unchanged in here? A catalyst. O3 goes in, O3 goes in. Do you see O3 come out anywhere? I don't see a catalyst. So not all reactions have catalysts, okay? So there's no catalyst. There's nothing that comes in and comes out unchanged. Now, an intermediate is something that is produced, so it's a product first, and then it is reconsumed, so it goes back in as a reactant somewhere later in the reaction. Do you see any element or substance that comes out and then gets reused back up? There is one, right? Who is it? Just plain monoatomic oxygen. It gets produced, but then it gets put back in. So it gets spit out, and then it goes back in. Produced and then consumed. By definition, that is what an intermediate is. Okay? Wow, I went much faster in here. So we're going to practice, and this is what we're ending with today. So mechanism 1, and this is the demo that I'm going to be doing for you guys on Friday, is a 2-step mechanism. And I'm going to do number 1 with you, and then I'd like you to see if you can answer all of these for number 2. So in each of the following mechanisms, determine the overall reaction, the catalyst, if any, and the intermediate, if any, okay? So how do you do the overall reaction? Well, let's practice again. For the overall reaction, we need to cancel out things on opposite sides because they don't participate in the overall reaction. Do you see anything that can cancel out on opposite sides? IO minus is a product right here, and it's a reactant here. It cancels. Anything else? The iodide I minus is a reactant, and then it is a product, so it cancels. So now what we do is for the overall reaction, we write what's left over. So there's H2O2 on the reactant side, and then there's another H2O2 on the reactant side. So there's 2 H2O2s, right? 2 H2O2s. There's one here, and there's one here, both reactants. H2O2, H2O2. Be careful, these are not H2O2, these are H2Os. H2O2 is hydrogen peroxide, H2O is water. So 1, 2 waters, right? On the product side. There's one here, and there's one here. And this guy is left untouched, right? That oxygen gas is also a product. So this is your balanced chemical reaction. This is your decomp. This is the decomposition of hydrogen peroxide into water and oxygen. So what's interesting is, most of you guys have seen hydrogen peroxide, right? It's that liquid in the brown tube or the brown bottle. If you've ever opened it up and like dumped it in a container, O2 is a gas, right? And if you dump it in a container and you stare at it for like, I don't know, an hour, are you seeing a bunch of O2 bubble out of it? Not usually, right? It just like sits there, and it would just like sit there in the container, meaning this reaction happens really, really slow. So guess how you could speed it up? What's one way? Heat it up. What's another way? What's another way we can speed up a reaction? Add a catalyst, right? So look at this. Is there a catalyst in this reaction? Is there a reactant that goes out or goes in at the start of the reaction and comes out unchanged? And yes. So it goes in to the reaction the same way it comes out. It looks the same. So oxygen does come out, but did it go into the beginning? So catalysts have to start off the reaction. That's the point, is you put them in at the beginning so that you can make the reaction go. But then they get spit back out unchanged because they do not participate in the chemical reaction. Look at the I minus. It goes into the reaction and it comes out unchanged. Iodide in the beginning, iodide at the end. That is your catalyst. Now, an intermediate is something that is produced in one of the steps and then gets used back up in a subsequent step. So do you see anything that gets produced and then gets used back up? The IO minus, very good. So IO minus, it gets produced in the first step and then it gets reconsumed right back in the second step. Now, it doesn't, if there are multiple steps more than 2, it doesn't have to get reused like right away. So it could get produced in the first step and then like reconsumed in a 4th step as long as it gets reconsumed. All right? So please try to answer. Oh, also notice these guys, your catalyst and your intermediate, are not part of our overall reaction. Okay? So please try to answer these, all 3 of these, A, B, and C, for mechanism 2 on your own. See if you can do that. Can you write out the overall reaction? Can you identify any catalysts or intermediates if there are any? All right, so hopefully you got SO2 plus 1/2, oopsies, whoa, O2 makes SO3. So this is our balanced chemical reaction. Our, oopsies, I'm just going to have to redo it. Our catalyst that goes in and comes out unchanged is V2O5. It goes into the reaction